So hello everyone, I am Vedant from Data Science and AI branch, batch to be graduated in 2026. So here I am to give my presentation on the topic of application of linear algebra. So the the most important application of linear algebra, as per what I feel, are graphs. So here is my presentation on graphs, because graphs are such a data structure which can be completely represented with the help of a matrix. So here let's begin with graphs. So first of all, what are graphs? Graph is just a set of vertices and edges, where the edges connect them, and we can represent those connections with the help of matrices. Now these matrices can be of various kinds. The most generally used matrix is adjacency matrix, wherein we represent any two nodes that are being connected as being one. So for example, if one and two nodes are being connected, then in the matrix, for the first row and for the second column, we would represent it via 1. And similarly, a matrix is generated based on our entries. Now, for my presentation, I would be focusing on a special kind of graphs which relates to the flow of quantities, and I would try to develop an application so as to further formalize it. So mostly my presentation would be based on electrical circuits and currents upon it. So here is the graph that I would be focusing upon throughout the lecture. This is just a randomly chosen graph, and it is a very small size graph, so as to maintain the simplicity as well as keeping the strength of the concept. And it is a graph that comprises of a total of n is equals to 4 nodes and m is equals to 5 edges, where the edges are directed edges, that shows the flow. So currently, suppose the edge 1, which is flowing from node 1 to node 2, represents that a current flow is there between node 1 and node 2. Now initially, for all my considerations, the resistance of the graph has not been considered, because currently in the equilibrium state, the v is equals to the IR term won't be involving them, and since the delta v is equals to zero equation will be solved, so the resistance would only act as a scaling factor for the currents. Rather, the equations won't be changed, as v2 minus v1 would be mostly zero. So let me begin it via representing it over a matrix. So first of all, let me talk about the application of everything that I am going to be talking today. So any flow model, for example, the hydraulic flow of, or the flow of water, or flow of oil, or even the flow of electrons in the various chemical models, such as the model of fullerene, of whose chemical bonding to be studied. For these kinds of models, the applications that I am going to be discussing today would be very applicable. And graphs are really an important topic in day-to-day life, because many different networks, for example the flow of roads, etc., can be mapped very easily using graphs. So to begin with, let me show you that how every graph can be represented with the help of an adjacency matrix. So the matrix that I am going to be taking here is this matrix. So let me first talk to you about what this matrix is, or rather I should just make the matrix on my own. So so for my matrix, every row would be corresponding to a unique edge of the graph. Every edge which is mapping, which is a mapping between, say suppose the first edge takes the charge from node 1 to node 2. So since it is transferring from, let me mark the nodes as well. So node 1 2 3 4. So since it is taking it from node 1, so a minus 1 to it, because it is losing the charge, and a plus 1 to node 2, and 0 and 0 for them. Now for the second edge, which is from node 2 to node 3, it would get a minus 1 here and a plus 1 here. And the third edge, which is this one, is taking from node 1 to node 3. Now very important part that I need to highlight here is that these three edges, the set of edge 1 followed by edge 2 and edge 3 alone lead to the same vertex, which is edge 3. In terms of linear algebra, how do we represent it? It is just like the same path, or the same combination of columns, and that could easily be verified as once you see this row 1 and row 2. So if you sum up these rows, then you may find that the result is exactly the same, and hence we can draw one very important conclusion, that traveling over path or traveling over edges is the same of is the same as summing the vectors or the row vectors, because via sum we can travel over multiple, we get the path that is traveled over multiple edges. This also has an application in the dynamic programming problem, wherein we are required to count the number of paths of, say, length k. So even there we can use the same concept of adjacency matrix, where the adjacency matrix to the power k represents the I comma jth column represents the number of paths of length k data from node I to node j, because from the dp problem you can compute that dpk minus 1 of I comma s sigma into dp1 of s comma j would be dpk of ij. The all paths of length k would be for any intermediate vertex s, if I travel from vertex I to vertex s with a length of k minus 1, and then k to j with a length 1. So this would give me the count of all paths with length j, which is, if you see carefully, this is just the value of dpk k minus 1 into dp1, where dp1 is the same as adjacency matrix, and hence this could be generalized that adjacency matrix to the power k gives the sum of paths of length k. And similarly, this is how much wide ranging linear algebra applications are. Like you can see directly that how linear algebra combination of columns and transformation from the adjacency matrix gave us so important results. Now let's get back to the original problem. So as you have seen that the set of edges, edge 1 2 and 3, form a cycle, and this is equivalent to they all the set of them represents the same path, or they are linearly dependent in terms of the language of linear algebra. So this is how cycle, which is a common term used in the language of graph, and linearly dependent, which is a common term used in linear algebra, are related in terms of their incidence matrix. Let's move further to the two other edges, which is edge 4 and edge 5. So edge 4 is from the first vertex to the fourth vertex, and similarly edge 5 is from the third vertex to the fourth vertex. This creates our entire incidence matrix. So now this matrix and this graph are exactly the same picture. Everything that this graph says can be understood with the help of this matrix, and anything this matrix says can be understood with the help of this graph. I mean, using any one of these you can make the other one. So now the basic question of linear algebra, the solution to the equation. Let's say ax equals to 0, where I am denoting a as this matrix that I have created right now. So for any linear algebra question, we are interested in finding the solution to x equals to 0, or this is same as null space of a vector. So we need a dummy variable x such that we can frame that. So I'm taking x1, x2, x3, x4 to be the variables. So the ax matrix would come out to be x2 minus x1, x3 minus x2, I need to find the solution of this, which is ax equals to 0. Now substituting any one variable, suppose x1, so I get x2 is equals to x1 from the first equation, and similarly x3 is equals to x2, and moving over all the equations, I get x1 is equals to x2 is equals to x3 is equals to x4 is equals to x5. This indicates straight away that all the values being same is a solution to it. Now let's see that what does it mean from the matrix. So if you see that any row is comprised of a single minus 1 and a single plus 1, so for any row and for matrix of any size, this statement has to be true, that uh, the vector 1 1 1 1 has to be a trivial solution to this system of equations for a matrix of any size n. Now what does these x represents? I forgot to tell you that these x's represent the potentials at various points. X1 represents the potential at point 1, similarly x2 at point 2, and the first edge which represents the flow through the first wire, it simply indicates the potential difference between them, which is x1 minus x2 or x2 minus x1. That would be covered via the sign of current. So similarly, all the rows, for example, the last row which corresponds to edge number 5, this is x4 minus x3 corresponding to the potential difference between the points 4 and 3. Similarly, as I have talked about that in different flow problems, the quantity would differ. For the electric case, it comprises of the potential term. So moving further in the study, since I have not included any battery in my diagram, but let me just talk about it briefly. Suppose if I have a battery over here, then the potentials that I would get over the sum of this all would even then turn out to be 0, because that's what KVL is. And we can prove it using the fact that how much the potential rises here would be equal to the drop in potential in the other node. And similarly, even if there are batteries involved internally in the circuit, the 11111 solution would always be a part of the solution. And for the trivial case also, it is a solution, and it is just saying that the sum of potential over all the loops, if taken, that would lead to the zero solution, which is the statement of KVL. Present the potentials of the x1 x2 up till xn are the potentials at nodes. When multiplied by a, we get x2 minus x1 and the various m different potential differences. Now along all these potential differences there are m associated currents which are linked by the formula delta V is equals to IR, or x2 minus x1 is equals to 1 by R is equals to y1, for example, only considering for the first one. And similarly y1 y2 I have a total of m different associated currents. So now let's look at a different picture which would involve y's. So since I have the A matrix, first let me have my graph. This is the same graph that we are working with. And this is the matrix that we had seen, which we had called the A matrix. Now let's make the A transpose matrix corresponding to this matrix. Okay, so for this A matrix, this is the A transpose matrix, and now what we are interested is to find the solution for A transpose y is equals to 0, or the null space of A transpose, or the solutions of A for the solutions for A transpose. So first of all, before solving it, what is the dimension of null space of A transpose? A transpose is a n cross m matrix, as A was a m cross n matrix. So dimension of null space would be straight away m minus r, because there are a total of m different edges or m different current wires and m minus r different different variables in the null space. So computing it would be 5 minus 3 is equals to 2. And now let's see what does A transpose represent, or what story does the role of A transpose represent. So for example, let me now consider the first row, which is minus 1 0 minus 1 minus 1 0. Let me first write it. I am trying to find the solution for y3 y4 y5 is the 0 matrix. So the first row represents minus y1 minus y3 minus y4 is equals to 0, and it is very easy to see that where does this equation come from. Let me show the second equation as well, and then let me show all the 4 equations and then we'll see it together. y2 plus y3 minus y5 is 0, y4 plus y5 is 0. So first of all, these are a total of 4 equations representing the 4 nodes, and now for the first node, the first current, third current and fourth current is going out of it, and that's exactly what this equation is saying: minus y1 minus y3 minus y4. And similarly y1 minus y2 for the second node, y1 coming in and y2 going out, and similarly for the third node, y2 coming in, y3 coming in and y5 going out, and y4 and y5 both coming in for the fourth node. So this is how they are all interdependent, where the A matrix was related to the potential differences. Similarly the A transpose, here the variables of A transpose are directly linked with the currents, which here I have represented using y. So after seeing this, let's see the applications of linear algebra into it. Mm, Let me now, first of all, let's see what happens. What is this called in terms of the language of electrical circuits? And this is a very well-known and famous law. This is known as Kirchhoff current law, which means that the sum of total currents coming in and going out into a single vertex, the sum of coming in and going out is zero, where the signs are adjusted accordingly, because the signs coming in and signs going out are not, I mean yi is not necessarily positive, it may be negative as well, but the same sign is followed throughout the problem to make the solution accurate. What how does this complete the picture? The A transpose when multiplied to the y matrix gives us the equation A transpose y is equals to 0, which is KCL law, and here these were linked to the KVL laws. So this is how linear algebra links the various branches of electrical circuits together. And let me give a more clearer picture to this term as well. So here we had x2 minus x1 and the various potentials xi minus xj written over here, which was for a given wire. So and we know that if we multiply it by a corresponding, say suppose 1 by r1, where r1 is the resistance in the first one, and similarly in all the diagonal entries up till rm, so then we would get the corresponding x2 minus x1 by r1 up till, and the last row was, I suppose, x4 minus x3 by r5, and these represents the currents i1 या फिर y1 as I have included in the second page up till y5. So here if this matrix which contains of the potential differences, if it is multiplied by R inverse matrix, where let me clarify what R matrix is. R matrix is made up of R1, R2 up till Rm is a diagonal matrix consisting of only on the diagonal entries being the resistance of the say the ith row and the ith column is for the ith wire what the resistance is, and R inverse would mean that for each and every element I am just having 1 by R1, and similarly. So that's how the various things are linked with the help of a matrix. Now the concept of dependence and independence. So for these columns of the A transpose matrix or the rows of A matrix, what I want to show is, say suppose the first row and second row are independent. I'm trying to find out three independent rows. So as the rank is 3, so minus 1 1 0 0, and similarly the second row is also independent, but the third row is dependent on the first two, as we have already seen it forms a cycle. So leaving that, the fourth row is minus 1 0 1 0. So this completes our entire set of the three vectors, and now let's see what it is. So this is this is comprising of the first edge, the second edge, and the fourth edge. Similarly, I could have skipped the fourth edge and have taken fifth as well, or I might have skipped two and taken third edge as well. But what I want to show you here is that these are set of three, या फिर R representing the rank, total number of 3 independent columns, or if the word columns of A transpose and rows of A, where we already know that each row represents a specific wire and each column of A transpose represents a specific wire. So this is what this is equals to. is a really important fact. If I take any other edge which would be dependent on each other, then it would create a cycle. So this is that in the total number being rank is the maximum number that I can take that would be linearly independent. And what it gives is a really is a important term in graphs. This is known as a tree. Tree is a subgraph of an entire graph in which no cycles are formed. And here also using those linearly independent columns of A transpose or the linearly independent rows of A, we form a tree. And similarly, suppose I might have not taken the A2th one, but I would have taken A3. This also forms a tree. Or suppose instead of A4 I would have taken A5. This also forms a tree. And similarly, each combination of linearly independent columns forms a unique tree. And this is how the spanning trees of a graph are directly related to independent columns of matrix A. Now A transpose. Now I want to complete the picture, this very picture wherein I am trying to solve the current equation using the various parameters. So for now I have taken care of the resistance terms via the R inverse. But there are also cases wherein say a wire has a current and an external current source has been added to it. Say suppose 2 ampere is being flowed into 2 and out of 1, which is externally supplied. So in the loop equations, instead of getting all zeros, the total sum of inside edges at node 1 has to be minus 2. 1 minute. It would be plus 2 because the excess current is being supplied out. And similarly, for the inside edges which is not part of the external source, for them in the for the second vertex it would be minus 2, as it is being supplied from externally. And hence when we add it to the external source current, which is a minus 2 here and a plus 2 here, we get a 0. So in order to take care of these terms, we add a I external term to our KCL equation, which is A transpose y is equals to I external. The signs would be taken care of according to the signs of y, and I external would be adjusted. And similarly, for the potential terms, we could also introduce external potentials between the nodes, and then the sum over say a specific loop won't be 0 but a non-zero value, and that would be adjusted by another constant Ax equals to E. So solving these various parameters, and similarly this is R inverse E is equals to Y, where the potential differences multiplied by the conductance are the currents. So taking care of all of it together using this equation gives R inverse Ax equals to Y, and now using Y here we get A transpose R inverse Ax equals to I external. I did not mention it here. So this is the exact solution of the electrical current problem or the Kirchhoff laws in all the conditions of external sources, as well as taking all the loops and conditions simultaneously. So yes, so now let's get back to the original problem that we were solving, which is to find the solution for A transpose y is equals to 0. First of all, since we have seen that the variables y represents the various currents that are flowing through the variables, and A transpose y means that the sum of all the currents entering at a specific node. For example, uh, this specific equation here, if this is equals to 0, implies at vertex number 1 there is no net accumulation of charge. So all the charge that is entering into this node is also going out. And similarly, the same pattern is being repeated for all the nodes. In order to find the solution, we already know that the dimension of its null space is 2. So we need to find two independent vectors such that their linear combinations would be giving us the entire solution. So to begin with, let's create a situation wherein there is no accumulation of charge. So I'll again copy the original graph. So now analyzing this graph. So suppose for the first solution, say one unit of current, say 1 ampere is flowing through the first node. So in order to achieve the conditions of KCL, 2 also has to have 1. And now for the division between 3 and 5, I can select any random number. But if I select a specific number that all the current revolves around this loop and no current flows in this direction, so for that I'll get current in the third node to be -1 and 0 0. So what does this represent? This represents that all the current is only flowing through this loop, and this is definitely a solution because all the charge that was coming out is going inside it and no charges is flowing in, and so this is definitely a solution for A transpose Y is equals to 0. Similarly, we notice another loop, so let's loop around this loop and applying the same law. So it is +1 for the third node, +1 for the fifth node, and -1 for the fourth edge. For the third and fifth edge we have a +1, and for the fourth edge we have a -1, and no current for the first and second node. So these two independent solution y1 and y2 are definitely solving our original problem that we had started with, that results in the solution of KCL. Now analyzing it further, at the elementary steps that we were taught in our basic classes, that we only loop through the smaller loops and not the big one loop. So let's see the reason through it in terms of linear algebra. So suppose we naively loop through the bigger loop as well. So doing that would give us 1 1. There is no involvement of the third edge. For 5 it is positive, for 4 it is negative, and for 5 it is positive. So this is what we get if we make a current loop throughout the entire edge and entire outer boundary, which is also a loop or cycle. But what we see here is, since this is a combination of two individual loops, we get the same dependence over here. So suppose if I add these two, so what do I get? I get a 1 1 0 -1 and 1. And to see that this is exactly what the big loop states. So in other terms, or in the language of linear algebra, I would say that the equation that I obtained through the bigger loop is linearly dependent upon the individual elementary loops. So therefore, by solving this bigger loop, I won't get any new equation but a repetition of the original equations that I have gained earlier. But one thing to notice here is that the number of small loops, which were 2 here, is directly number of loops is directly associated or in fact equal to the dimension of null space of A transpose, where A was our incidence matrix. So using this knowledge, as the total number of extra loops would be contributed by those edges that are not necessary for the tree that I have showed earlier. So analyzing this further, since we have already gained this equation, which is dimension of null space of A transpose is M minus R. So let's further analyze it. Dimension of null space of A transpose is equals to M minus R, as there are a total of M columns, and since we know that rank is, let me write in terms of words. So M is the number of edges of the graph and rank is n minus 1, where this n is the number of nodes, and this is exactly equal to the number of loops, and this gives us a really important relation that is not seen very easily. Further analyzing it, n minus 1 is the required number of edges that is required for forming a tree, but there are a total of m edges. It means m minus n minus 1 edges are extra than the required tree. So hence those extra edges would result into formation of individual loops, and this is the real identification of this. But let me show its another counterpart, where does it relates to topology. So the number of I am just rearranging the terms. The number of nodes minus the number of edges plus the number of loops is equals to 1. And this is what is called in topology the Euler's formula, and this is true for any graph, and it is not only true for planar graphs, but it extends much further, and therefore this is how linear algebra extends to many domains, even up till topology, where it's the solution to the dimensionality problem leads us to a really important result derived by Euler. And we have even seen that the outer loop is just a linearly dependent column. So this is how the various elements and the various fundamental columns, like the null space, A matrix, A transpose matrix, the dimension of the various matrices, and the terms in graphs, for example the number of spanning trees, the total number of edges, the total number of cycles, etc., relate to each other, and what are the conditions, how is the dependency of linear independence and its relation with respect to trees, and linear dependence and its relation with respect to cycles. So this is how it all relates. So now I am going to demonstrate it on a sample problem. So here I have a sample graph upon which I am going to apply the same concepts that I have shown right now. So let me call the matrix A, which is the incidence matrix of this graph. So since there are a total of 6 edges, so let me I forgot to label all the edges: 1 2 3 4 5 6. So here are the edges. So one by one, let me try to find out the incidence matrix, and then we would also be finding out what is the null space of A matrix and the null space of A transpose matrix, such that it helps us to generalize and even find these these concepts really quickly for any matrix. We can do it by the normal method of row substitution, the elimination method that we study in linear algebra, but using the graph concepts and the basic concepts we can do it much simpler. So to begin with, for the first edge, let me label the edges as well. So uh, this is for edge number 1, this would be for edge number 2, 3, 4, 5, 6, as I have a total of 6 edges and I have a total of 5 vertices. So the first edge is from vertex 1 to vertex 2. And the second edge is from 2 to 3. The third edge is from 1 to 3. Fourth is from 2 to 4. Fifth is from 5 to 3. And sixth is from 4 to 5. And remaining all entries would be the trivial value 0. I need not even specify that. Because the corresponding edges do not touch the vertices. For example, this 0 represents that the sixth. Wait a minute. I do not actually need this sixth vertex index because there are only 5 vertices in my graph. So for example, this very 0 indicates that there is no relation between the sixth edge and the third vertex. So for the sixth edge, which is over here, and the third vertex is here, and therefore they have no connection directly. So now let's move on to the problem, the null space of A matrix. And here also we can see the same intuition that this would turn out to be x1 minus x2 or any xi minus xj terms in all the columns, because there is only 1 plus 1 and 1 minus 1, and solving that would lead to a constant value for all the different vertices. So that could even be seen that the sum of elements throughout all the rows is 0, and therefore the same solution 1 total of 5 edges applies here as well. And if we want to find any further solution, then seeing that if we take any four independent columns, then any 4 columns, then they are linearly independent. And this is also the same to the fact that tree always has n minus 1 edges. So there are at max n minus 1 edges, and here the n minus 1 condition is again being satisfied. For example, let's use the first 4 columns only to show the linear independence. So these two rows need to add up if we want to make the suppose we want to show that c1 plus c2 plus c3 plus c4 is equals to 0 has if we want any linear combination, then the coefficients has to be 0. And showing that would mean that we need to add all of them together for this row and this row, this row and this row. The first row means that we need to take the linear sum of them. But when we do that, the fifth and the sixth column won't be 0, and hence it is not the 0 solution even if we try to satisfy the first 4, and hence they are linearly independent, and the dependency that we tried to prove is wrong. and therefore hence we have deduced that the rank is at least 4 because the first 4 columns are independent, and since we already have an element in the null space, we can very surely say that the rank is exactly equals to 4, which again matches the n minus 1 edges fact that was shown earlier. And now moving on to the A transpose matrix, if we want to find out the null space of A transpose, that just means that it is trying to get the solution for A transpose y is equals to 0, where if where we want the sum of currents with sign at a specific node to be 0, which is the same statement as the KCL. Again we follow the same methodology, that if we assume certain current moving here and we try to maintain it over a loop, so over here and over here, so that would give us that would be one of the solutions in the solution set. So one for the first and second edges, minus 1 for the third edge. This would be one solution. There are a total of 6 edges, and similarly if we try to get a current loop in this region, so that would mean a plus 1 for 4, 5 and 6 and a minus 1 for 2. Yeah, and a plus 1 over here for the remaining values. Since the rank is equals to 4, it means that rank is equals to 4, and there were a total of 6 possible, at max 6, and we have found 2 elements in the null space. So therefore we have found all the elements, because there could be at max 2 linearly independent y in solution of A transpose y is equals to 0. Now that we now let's move to the next part, which is to prove the topological relation, which is the sum of nodes minus the number of edges plus the number of loops. So the most easier thing, which is the number of loops. So number of loops is 2, number of vertices n is equals to 5, and the number of edges m is equals to 6. Now what the relation was, we want to get the sum of nodes plus loops minus edges, which is 2 plus 5 minus 6, and this exactly comes out to be 1. So hence the formula that we had derived earlier and the Euler's original relation is also valid over here. Let me ask, here is another interesting question. What is the value of sum of entries of A transpose A? So if we look at the value of A matrix and A transpose A, we get to find that every edge A transpose A is just the sum of dot products of the corresponding vectors. Now in order to find their values, since the values are only of magnitude 1 or 0, so the values would be only the sum of all the non-zero entries of A. And since we know that there are a total of 6 edges, and each edge corresponds to 1 plus 1 and 1 minus 1, so each edge corresponds to 2 non-zero entries. So the value of sum of all entries of A transpose A would be 12. I hope so this explanation was sufficient for you to apply linear algebra concepts to graphs and appreciate that how how important linear algebra is, applying its domain throughout all over mathematics. Thank you so much for your patience listening.